an electron scattering off a proton. Simple enough, right? A proton comes in, the electron absorbs it, continues on its way, and emits a new proton. We call this the scattering of matter. But when we make the diagrams and calculations for scattering, we must include some peculiar possibilities. The electron could emit a proton before absorbing one. Already strange. But there's something even more bizarre lurking in the mathematics. The electron emits a proton. Then, and this is the really odd part, travels backwards in time to absorb a proton, and then proceeds forwards in time again. Yes, backwards in time. It's not as some theoretical abstraction, but as a real, measurable phenomenon. The path of such a backwards-moving electron can be so long as to appear real in an actual physical experiment in the laboratory. Think about that for a moment. We're not talking about mathematical tricks or convenient fictions. We're talking about something you can detect, measure, verify in a lab. When you observe this backwards-moving electron, while time moves forward for you, here's what happens. The backwards-moving electron appears the same as an ordinary electron, except it's attracted to normal electrons. We say it has a positive charge. For this reason, it's called a positron. The positron is a sister particle to the electron and is an example of an antiparticle. And here's where it gets truly profound. This phenomenon is general. Every particle in nature has an amplitude to move backwards in time and therefore has an antiparticle. Every single one.
Please subscribe this channel for more videos.
Long before anyone understood why, Dirac predicted that in addition to electrons there must be another particle called the positron. This was later discovered by Anderson. Dirac simply followed where his equations led, even when they seemed to predict something impossible. All the properties of these two particles obey certain rules of correspondence. The energies are equal. The masses are equal. The charges are reversed. But more important than anything, when they come together, they can annihilate each other and liberate their entire mass in the form of energy gamma rays. This wasn't just a theoretical curiosity. When Anderson found the positron in cosmic ray experiments, it confirmed Dirac's wild prediction and opened up an entirely new way of thinking about particles. The mathematics had predicted reality before reality revealed itself. It was clear that all particles should have corresponding antiparticles. For the proton, there should be an antiproton, with the same mass but opposite charge. The most important feature is that a proton and an antiproton can annihilate each other. People often get confused about neutral particles like neutrons. They ask, how can a neutron have an opposite charge? The misunderstanding is thinking that anti only means opposite electric charge. In reality, all properties are reversed. If we bring two neutrons together, nothing special happens. But if we bring a neutron and an antineutron together, they annihilate each other, releasing a tremendous explosion of energy. Because neutrons have significant mass, the energy released is enormous, producing a shower of particles and radiation. This leads to a fascinating possibility. If we have antineutrons, antiprotons, and positrons, we can, in principle, make antiatoms. But the physics allows it. Only engineering challenges stand in the way. Consider hydrogen, a proton with an electron orbiting it. Now imagine antihydrogen, an antiproton with a positron orbiting it. Would it work? Yes, the forces are identical. The masses are the same. Quantum mechanics governs antimatter exactly the same way. A clock made of antimatter would tick exactly the same as one made of matter if kept separate. Brought together, they would annihilate. However, physics discovered something shocking. Left and right are not equivalent. Experiments involving beta decay showed that the weak nuclear force violates mirror symmetry. The universe distinguishes left from right. This raised a deeper question. How does antimatter behave with left and right? Experiments showed something beautiful. Matter to the right behaves the same way as antimatter to the left. The symmetry wasn't destroyed, it was hidden. This combined symmetry is called CP symmetry. The universe respects this deeper symmetry even while violating individual ones. This discovery has profound implications even for communicating with alien civilizations. Using beta decay experiments, we could define right and left using pure physics. If aliens were made of antimatter, their definition of right would be opposite to ours. If such beings ever met us and reached out with the wrong hand, one touch could annihilate both matter and antimatter in a burst of gamma rays. At the heart of reality lies a continual cycle of creation and destruction. When particles and antiparticles collide, their mass converts entirely into energy. The process is reversible. High-energy protons can create particle-antiparticle pairs. Protons themselves are special. A proton moving backward in time is indistinguishable from one moving forward. That's why protons are their own antiparticles. The idea that antiparticles are particles moving backward in time explains why they must exist. Pair production and annihilation are not creation or destruction, but a single particle making a U-turn in time. The electron never truly disappears, just changes direction in time. Strange as it sounds, this picture works perfectly. The calculations match experiments to astonishing precision, precision better than 1 part in a trillion. Every Feynman diagram relies on this interpretation. Nature has spoken. Particles can and do move backward in time, and we call their backward-moving versions antimatter. The universe is stranger than we imagine. That's what makes physics so wonderful.